on the topic of triple integrals. So now we are interested in extending the idea to triple integrals. Consider the following box. How do you find the volume of this box? Well, in the context of calculus, we can define the volume as the volume of a closed bounded region D in space is triple integral of dV, which is the element of volume, over region D. In that case, you have the measurement for x-axis, you have the measurement for y-axis, and you have the measurement for z-axis. This is basically the length between 0 and 4, the length between 0 and 4, the length between 0 and 4, and when you multiply these together, you basically find the volume. But in this case, you have the definite integral for each case. We have a nice theorem. The theorem, which we extend from the iterated integral, double integral that you saw before, is our famous Fubini's theorem, which is now for triple integrals. The triple integral of a continuous function like f of x, y, and z. So please note that here we have 3 free variables. It might be the temperature function or anything else over a box, which is denoted by the closed interval x ranges between a and b, closed interval c and d, which is basically saying that y is bounded between c and d inclusive, and finally it says z is bounded between p and q inclusive, is equal to the iterated integral. You have triple integral of f of x, y, z dv over box B, which is, you're going to copy down the function itself. Then the inner integral can be taken with respect to z, but z is bounded between p and q. Then you can take the integral with respect to y, but y is bounded between c and d. And eventually, you're going to find the integral with respect to x, but x is bounded between a and b. So if you have a box, or if the boundaries are fixed values, we can apply the Fubini's theorem from the double integral to triple integrals. Example for you. Question says, evaluate the triple integral of x, y, z squared dv over box B, and B is defined as a rectangular box, the set of all points x, y, z in the space such that x is bounded between 0 and 1 inclusive, y is bounded between -1 and 2 inclusive, and z is bounded between 0 and 3 inclusive. Let us begin, everybody. The triple integral of x, y, z squared dv is equal to, we're going to copy down the same function. We're going to take the integral, for example, with respect to x. Nobody's stopping you. You can switch this around, but make sure you have a correct integral associated to what you are integrating with respect to. So here I'm going to take the integral with respect to x first, but my x is bounded between 0 and 1. Then I'm going to take the integral with respect to y. Y is bounded between -1 and 2. And then I'm going to take the integral with respect to z, and z is bounded between 0 and 3. Note that none of these x, y, and z squared, they are connected together by addition or subtraction. And note that all of these boundaries are fixed values. So basically, you can separate these into 3 integrals, or you can continue taking the integral as you know before. We're going to apply the integral of u to the n du, which is u to the power n plus 1 divided by n plus 1 plus constant of integration. N cannot be equal to -1, otherwise you get the denominator equal to 0. And remember that for definite integral, the constant of integration disappears or vanishes. Let us begin, everybody. This is equal to, well, here you have the integral of x, y, z squared with respect to x. So you end up with x squared divided by 2. Your x is bounded between 0 and 1. Then you're going to take the integral with respect to y, then with respect to z, or you could separate these as well. Either is fine. This is equal to, if you plug in 1, you get 1 squared yz squared divided by 2, or yz squared over 2. And 0 doesn't change this. It's going to be 0. So we don't need any extra term here. Then the integral with respect to y is bounded between -1 and 2. Then you take the integral with respect to z. Z is bounded between 0 and 3, which is basically equal to, here you have the integral of yz squared divided by 2 with respect to y. You're basically following the same formula that we did before. It is y squared z squared over 4, and y is bounded between -1 and 2. Then we take the integral with respect to z. So all of these are definite integrals. You need to plug in 2. Then you need to plug in -1. This is equal to 3z squared over 4. If I plug in 2 here, I get 4z squared over 4 minus -1 to the second power, which is 1z squared over 4, which is 3z squared over 4. We're going back to the formula that we used before. That's why I use u in general. So you can substitute any variable x, y, z, t, anything you like here. This guy is equal to z cubed divided by 4. Z is bounded between 0 and 3, which is 3 to the second over 4, or 27 over 4. So to evaluate the triple integral of x, y, z squared dv over a rectangular box, you can switch these around. It doesn't matter if you take the integral with respect to y first, with respect to x first, with respect to z first, you get the exact same result. You can switch these around. The boundaries are fixed, and there is no connection between x, y, z squared in terms of addition or subtraction. Or initially, you could separate these into 3 integrals and then do the calculation and finally multiply all of these together.